Hello and welcome to Honors Function. This is the second lecture on the local behavior of a polynomial function, and we started looking at the behavior of the graph of a function around its x-intercept. We are going a little bit further in this lecture by looking at a tool that will allow us to detect the presence of x-intercepts of a polynomial function. I said detect the presence, not find it. Okay, and you will see the difference. This tool is called the bisection method and sometimes the dichotomy method. It is solely based on the continuity property of a polynomial function and therefore is also valid for any continuous function, not just polynomial. You can apply the tool to any function that is continuous. Let's begin. We'll start with a result that is fundamental in math, and in fact this theorem buttresses the most important result in differential calculus. So the importance of this theorem can hardly be understated. Very, very important. Okay, what does the theorem state? It states that if you take a continuous function, so for us, it's going to be a polynomial. We know a polynomial is continuous. If you take a continuous function, and if you take two inputs in the domain of the function, so for us, the domain of a polynomial is going to be all real number. Okay, we've already stated that. Then, here's the theorem. F takes all the values between f of a and f of b. Okay, and this is solely based on the continuity of the function. What doesn't mean that f takes all the values between f of a and f of b. That means if I take any value between f of a and f of b, so if p is such that, let's say f of a is smaller than p, which is smaller than f of b. Okay, we could also have the other way around, right? F of b is smaller than p is smaller than f of a, right? It could also be in this order. Then, what doesn't mean that f takes all the values? Then there is a c between a and b, such that f of c is equal to p. Okay, let me show you graphically. Maybe right now you're starting to understand, maybe not. Let me show you graphically what's going on here. So I'm gonna take a function that is continuous. So for example, something like this, it is continuous, right? And I'm gonna take two input. Here's a and here's b right here. Here is f of a and here is f of b right here. Now if I take any value between f of a and f of b, so for example let me take it here, p. Okay, if I take any value between f of a and f of b, I can't find a c between a and b. I can't find a c right here such that f of c is equal to p. F actually will take all the values between a and b. There is not a single value that f cannot take. Let me try to show you a counter example here. Maybe it will allow you to understand better. Check it out. If I want a counter example, I need to take a function that is not continuous. So I'm going to take a function right here that is not continuous. For example, here's a piecewise function. Here we go. And here I'll take it there. All right. So this is a function that is not continuous, right? Let me take a right here, and let me take b right here. Where is f of a? F of a is right here. And where is, I've lost my axis, right there. And where is f of b? F of b is right here, okay? And I've lost it again. Shoot. Here we go. All right, f of b. and here is f of a. All right, now let's take any value between a and b. Well, I'm not going to take any here. I'm going to take a specific value for which I don't know. It's not going to apply. So let me take, for example, this one right here. And again, I've lost it. What's going on here? Here we go. That was my little scribbling here. And then I took this value. Don't disappear. Thank you very much. Here we go. Let me take this value. You cannot find a c between a and b so that f of c is equal to p. That is not possible, right? Of course, if p is here, okay, I've lost it, it doesn't matter, okay. If p is here, yeah, I can find a c there. And if I take p there, I can also find a c. The problem is I have a large gap right here, and if I take p anywhere in this gap, there will not be an x that will go to that p, okay? All right, let's go, let me show you another example. Actually, this time we can take a very specific function. These were just illustration. Now, let's take, for example, the function f of x equals x4 minus 2x cubed plus 7x squared plus 8x minus 5, right? Let's take this function. Now, I plugged in my calculator and I found that f of 1 was actually 9 and f of 2 is actually 39. All right? So let me take a value between 9 and 39. So I'll take, for example, 30. I know I can find a c between 1 and 2. There is a c between 1 and 2 such that f of c is equal to 30. Let's check it out with the calculator. I've already plugged the function in the calculator into y1. Look at the graph of this function in the right window. So my tick mark on the y-axis are going by 5. So this is 10 right here, 20, and 30. Look, let me do a trace. I'm going to trace my graph. Where am I? I'm right there at the bottom. And look, you see, it's actually moving very, very continuously. And at some point, like right here, I know there is an I'm between. You see, this is 1 and this is 2, right? So I am between 1 and 2, and actually, if I look at this value here, this is 1.77, while this is 1.8. So between 1.7 and 1.8, I will have the right y, okay? This is called the intermediate value theorem, fundamental in mathematics, okay? Let's go to a corollary of the intermediate value theorem that is as important as the theorem itself. Okay, so here's a corollary. What does it say? It says if you take a continuous function, f is continuous, and if f of a and f of b have different signs, that means what? That means, I don't know, it can happen in two ways, right? Either f of a is positive and f of b is negative, right? Or f of a is negative and f of b is positive. F of a is negative and f of b is positive, okay? Then, if they have different signs, okay, then, okay, so if, then f has a root in AB. F has a root in AB, right? If they have different sign, look, graphically it really makes sense, right? If they have different sign, for example, if f of a is going to be right here, right? And I will take a right there. And let me take f of b right there. F of b is going to be right here, and I will take b right there, for example. Okay, so here we go. Here's a point of the graph, and here's another point of the graph. Now, the fundamental hypothesis is that f is continuous. Well, hey guys, if you want to draw a continuous function between these 2 points, at some point you're going to have to cut the x-axis, and that is where the root will be. Okay, why is it a corollary of the previous theorem? Because the value I'm going to take here is p equals 0. Okay, I'm going to take p equals 0 right there. P equals 0. Oh my gosh, everything is gone. Okay, right here. Okay, I will take p equals 0, and I will have a c, so that f of c is equal to 0, and c, of course, is called a root. Let's go over the first example before I present to you the dichotomy method, the bisecting method, bisection method. Okay, example number 1. Okay, example number 1. I want you to find the output of f. So here's the way I'm gonna present that. Okay, I'm gonna do a table here, f of x right there. I'm gonna plug that in my calculator, which I already did, and I want the output at -2, -1, 0, 1, 2, and 3. Okay, and I want you to tell me in which interval you can find a 0 of the function. So look, I've plugged this function into actually y3 right here. So let me not plot that in my table, but on the other hand, I do want to see y3. So I'm going on top of the equality and I push enter. Let me check out the table of values. I start at -2, right? So it is -41, -11, -3, -5, -5. Let me start writing or I'm going to forget. -41, -11, -3, -5, -5. No, I think I've made a mistake. No, that's correct. 9 and 49. 9. Okay, here we go. All right. What do we want? Let me check though. Yeah, that is correct. What do we want? How are we going to know where we have a 0? Well, to have a 0, I need a sign change in the output. Do you have a sign change here? No, they're both negative. No sign change, no sign change, no sign change. And here is a sign change right there. There is a sign change in the output. Therefore, there is a 0, 0 in the interval 2, 3. And because I know it's not 2, right? F of 2 is not 0. I can open the interval. There is a 0 in 2, 3. All right. So now I detected a 0. This, the intermediary theorem allows us to detect only a specific type of 0. You know there are two ways to have a 0, right? You can cross the x-axis or you can bounce on the x-axis. Now this theorem, the corollary of the intermediate value theorem, it's a corollary of the intermediate value theorem, is a bit crude. It's not very subtle. It only detects the 0 where you have a sign change. If you don't have a sign change, right here, look at f of a right there. F of a is going to be positive, and here it doesn't matter how close you are, but f of a will also be positive. There is no sign change for an even multiplicity. Okay, so the corollary of IVT only allows us to detect 0 of odd multiplicity. So now let me show you the dichotomy method. Let me explain to you the dichotomy method. Okay, first of all, how can you measure a sign change? How do you know when f of a and f of b have a different sign? Have a different sign. What can you do? How can you assess that they have a different sign mathematically with a formula? If you were to write a program, how could you assess that two outputs have a different sign? Think. Well, it's pretty simple. It's called multiplication. Here we go. You do the product. If the product is negative, they have the same sign. If the product is positive, they have a different sign. Okay? So what is the dichotomy method? So the dichotomy method is very simple. Here we go. Look. Suppose you have your A right here and you B like right there. Okay? Suppose you have A right here and B right there. Then f of A times f of B would be negative, right? Then what do? Then you cut the interval in half. Okay, so you define C to be A plus B over 2. And so the next step is to do f of A times f of C. Now, in this case, f of A times f of C would be positive, right? They both have the same sign. It's positive. Therefore, the solution lies not in AC but in BC. The solution lies in BC. And then what? And then you get another one and you get a D right here, and you do D equals C plus B over 2, right? You take the middle. It's a middle. Dichotomy. It means, I believe, dividing in 2, okay? Then you look at that, and then you would do f of C times f of D. You do f of C times f of D. And in this case, f of C times f of D would be negative. They both have a different sign. So the solution lies in CD. the solution lies in CD, and you keep dividing in 2 until the distance between C and D is as small as you want it to be, like 10 to the negative n, and then you would approximate the solution, you would know the solution with n digits after the decimal points, for example. Let me show you what I mean on an example that I have done in my notes. So let's take a look, for example, at this polynomial function right here, degree 5, okay? I've plugged it in my calculator. Let me look at the table of value. Here's the table of value of this function right here. So we can see that there's no sign change, right here. Look at -4 and 370. There is a sign change right here in the output. Therefore, between 3 and 4, I know I have, so between 3, f of 3 times f of 4 is negative. So I know there is a 0 between 3 and 4, between 3 and 4. Okay, so now I'm going to go on my home screen right here, right? And I'm going to do y1 at 3, y1 of 3, times y1 of 3.5, y1 of 3.5. Because I know there is a 0 between 3 and 4, two things can happen here. Either this product is positive, and I know the 0 will be between 3.5 and 4, or this product is negative, and I know the 0 will be between 3 and 3.5. So I'm only interested in the sign. It's negative, so now I know that my 0 is between 3 and 3.5. Okay, so now you have to go in the middle right here. The middle is 3.25. So let me do it again. So let me grab my previous entry right here. And instead of 3.5, I'm going to put 3.25 right here. Okay, and let me check out the sign. And the sign is negative again. So therefore, I know my 0 is between 3 and 3.25. What is the middle now between 3 and 3.25? It's 3.12.5. 125. Okay, so let's do it one more time. So I'm going to take this previous entry right here, and I'm going to do 3.125. Insert 1 right here. And what do we have? And we have again another negative value. It doesn't always have to be negative. Okay, at one point I'm sure it's going to change. So now we know the solution is between 3 and 3.125. Okay, that's 3.0. I'm still not sure of the first decimal after. Okay, I don't know if it's 3.0 or 3.1. I need to go further. The problem here is that I don't know what's the middle. So 3 plus 3.125 divided by 2, I don't know what's the middle, is 3.0625. Okay, so let me do second enter right here, and let's take 3.0625. So 0625 right here, and it is again negative. Oh, I got my first digit after the decimal point. Okay, I know it's between 3.0 and 3.0625. All right, good. So I need to take the middle again. I would like the middle to change and not be at 3 all the time. So let me do 3 plus 3.0625 divided by 2, and that is 0.312. Okay, so I'm gonna do second enter. Let me check out. So what do I want? 0.3125, 0.3125 right here, and oh, it's negative again. Okay, so this is an example I've done in my notes. Let me see how far we go. So let me go to my notes now. So if I look at my notes, which I've done, you have to go to the next step. Actually, it would have been in the next step where we take the middle right here between 3 and 3.03125, that we would have found a product to be positive. So at this point, you know the solution to the 10th. Okay, so that's to the 10th to the -1, right? You know the solution to the 10th. If you want to know it more precisely, you got to keep on dividing. let me see, it's still to the 10th right here. Let me see, and I am still to the 10th right here. Wow, you gotta go really far. Oh, right here, right here. I know it's 0.273, 0.29. Okay, so the solution is 0.3.02. Okay, and I'm saying it takes 2 more steps to get the 3rd digit fixed right here. You can write a program and you can count the number of steps. I did it with a calculator actually as some years. We won't have time to do it this year, but it's kind of interesting. You can write a program and ask the program to stop when the difference between the 2 boundary right here, so cn plus 1 minus cn, whatever the sequence is smaller than 10 to the negative whatever, what you want to assign, okay? And you can count the number of steps. This is a fine method and you can go really far. The problem with this method is that it takes a lot of memory in programming and it's very, very slow. It is not the method that your calculator uses. It could have been, but it's not. The method that the calculator uses is based on calculus. This method is not based on calculus. That's it. Thank you for watching.